So I think we'll get started. As I said, this session is about HA and FT. This is the standard disclaimer slide. You've seen this before. So I wanted to begin by presenting some context. Oh, I'm sorry. I forgot to tell you who's speaking. So my name's Keith Farkas. I'm a senior staff engineer at VMware. I work on the HA team. And my co-presenter is Jim Chow. He's a staff engineer on the FT team. So as I was saying, I wanted to start by giving you some context. So both vSphere HA and fault tolerance can be used to minimize unplanned downtime without the cost and complexity of traditional clustering solutions. Both are easy to use and can be enabled with a small number of mouse clicks. When used together, they protect against failures at 4 layers in the application stack. Those are shown here: the hardware layer, the virtual machine layer, the guest OS layer, and the application layer. At the hardware and virtual machine layers, infrastructure HA will protect against host failures, network failures, and VM failures by restarting the affected VMs, yielding minutes of downtime. Fault tolerance protects against similar failures, except there's no downtime. When a failure affects the primary VM of an FT pair, the secondary VM will take over with no loss of state or interruption in service. Now, looking at the guest OS and application layers, the HA feature VM application monitoring protects against failures at that layer. Specifically, if the guest OS crashes or hangs, the HA will restart the VM, meaning it will reboot the OS. Similarly, VM application monitoring provides some APIs. These APIs can be used by partners and users to create solutions for ensuring the availability of individual applications. So you can write an agent that runs inside the guest, for example, and it will be able to issue heartbeats to VMware HA layer, and if those heartbeats stop, the VM gets reset. So one solution in this space is offered by Semitech. It's called Application HA. So this session today presents a view of today and the future. I will begin by presenting an overview of HA 5.0, and then Jim will be presenting a technical preview of work we're doing on fault tolerance to enable it to be used with VMs having more than one virtual CPU. So my objective for this part of the talk is to have you learn about the enhancements made in 5.0 for HA, for you to understand the new architecture, and also, since I cannot go into all the details, to identify questions that you can have so that you can get those answered after the session. So let's talk about what is vSphere HA 5.0. So in 5.0, we completely rewrote HA. So if you're familiar with the concept of AAM, primary, secondary roles, where the log files are located, all those details are no longer apply. 5.0 was written with 4 objectives in mind. The first was to simplify setting up and configuring HA clusters. So I have a question for you. How many people have had trouble with DNS when configuring HA clusters? Okay, well, the good news for you is DNS is no longer required. The HA agents use only IP addresses. In addition, the agents are now pushed out in parallel and configured in parallel. So the net result is if you have a cluster of 32 hosts, it takes at most 2 minutes to configure that cluster. This compares to, in 4.1, it took approximately 1 minute per host. So it's approximately a 30 times speed up for a cluster containing 32 hosts. Finally, the configuration of the agents is much simpler, so you should not have nearly as many problems as you had previously with the configuration failing when you're trying to enable HA on a host. The second objective was to enable more flexible and larger deployments. So in 4.1 and earlier releases, we had this notion of HA agent primary role. That primary role imposed a number of restrictions that made it rather challenging to deploy clusters of sizes greater than 8, especially if you're worried about tolerating various hardware failures. So in 5.0, we removed the concept of primary, secondary roles. We removed the concept of, we removed only supporting 4-host failures, and we also eliminated the need to treat certain hosts in your cluster specially. In addition, the architecture scales much more. So these factors combined gives you much greater degrees of freedom when you went to go deploy HA. Now, while the architecture was designed to scale to a much larger number of hosts, in 5.0 we only support 32 hosts per cluster. The third objective was to make HA more robust and easier to troubleshoot. So perhaps the most noticeable feature here is that we've improved the isolation response to reduce the likelihood that you'll have a total cluster isolation event if you should happen to lose all the networking in your cluster. We've also improved, because we're using different agents, we have a different inter-agent communication mechanism. The net result is that it's much less likely you'll see interruption in the communication between the agents, and therefore you'll have much less problems with HA errors just suddenly starting appearing in your environment. Regarding troubleshooting, we've introduced more fine-grained HA host state, so that gives you more insight into the availability condition on your hosts. We've also improved the error messaging and made some changes to the UI to better expose the conditions of your cluster. And finally, a fourth objective was to fully support network partitions. So a network partition occurs when you have a group of hosts in your cluster that can communicate over the management network, another set that communicate over the management network, but both sets cannot communicate with each other. That type of failure is now fully supported in 5.0. Now, as what I've just said probably gave you the idea that the architecture is fundamentally different, and indeed it is fundamentally different. So my objective today is to tell you about the three key concepts in the new architecture and show how they come into play when a host failure occurs. Okay, so as I said, there's a new agent. The new agent is called the Fault Domain Manager. This agent implements all the on-host functionality for HA. There's no longer AM, there's no longer HA code in VPXA. The HA agent is a standalone agent and implements all the functionality. Now, what is the same? Well, the general behavior of HA is the same. You configure HA using vCenter Server or VC. You use vCenter Server to monitor your cluster. When a failure occurs, the failure is processed by the agents on the host independent of the state of VC. And the FDMs communicate over the management network. Okay, so now let's look at two of the key concepts. One of FDM roles and responsibilities, and the second about inter-FDM communication. Okay, so in 5.0 we have two HA agent roles, master and slave. Any FDM can become a master. A master is selected through an election. Normally you're going to have one master in your cluster, and all the other agents are going to assume the role of FDM slave. So in this figure here, shown here, we have 4 hosts interconnected by a management network. 3 of them are shown in blue, that represents the FDM slaves, and 1 is shown in green, that represents the FDM master. Now the master has specific and special responsibilities. It's in charge of monitoring the health of all the VMs and hosts in the cluster. If there should be a failure, it's in charge of orchestrating the recovery from that. So if a host fails, it will restart the VMs that were running on that host. It might restart those VMs on its own host or the other hosts. It's also in charge of reporting to VC the state of the cluster and reporting any failover actions to VC. And finally, it manages the persisted state. Slave has some specific responsibilities as well. First of all, it's in charge of sending critical updates to the master. For example, it must tell the master how much capacity it has available. The slave also restarts VMs as directed by the master. Finally, if the master should fail, the slaves are responsible for electing a new master. In addition to these responsibilities, both the master and slaves have some general responsibilities. They monitor the health of the VMs running on their host, and they implement the VM application monitoring feature. So let's talk about a master election now. So generally, an election occurs whenever a set of FDMs are not in network contact with a master. So when you first enable HA on a cluster, you're going to have an election. And in this example here, host 2 is elected to be the master. You'll also have an election if host 2 becomes inactive, or if HA is reconfigured on that host. Host can become inactive, it's put in maintenance mode, it enters standby mode, it gets rebooted, or it's disconnected. A third case where you have an election is when you have a network partition. So in the example a minute ago, we had host 1 is the master, but now we have a network partition. We ended up with host 3 and 4 in a separate partition. Well, they have no master in that partition, so they elect a new master. When a partition resolves itself, all but one of the masters will abdicate, and so you're left with one master again. So this is why I said initially Normally, you have one master in your cluster. If your cluster's been partitioned into 3 parts, you'll have 3 masters. So the master election takes 15 to 25 seconds, with the variance depending upon the reason for the election. When a new master is elected, it picks up where the last master left off, so there's no state that gets lost when an election is held. The host that has the greatest number of mounted data stores is elected the master. If there's a tie, we break it using the host IDs that are assigned by Virtual Center. Okay, so I've covered sort of the basics here: FDM roles, responsibilities, master slaves, and election. Next thing I want to talk about is inter-agent communication. So, as in earlier releases, the agents communicate over the management network. Unlike in earlier releases, the agents also communicate using the data stores. So data stores are used whenever the agents cannot talk over the management network. And specifically, they're used when hosts are isolated or partitioned. And I'll go into that in more detail in a minute. So let's talk about network communication first. The agents communicate with point-to-point. There's no broadcast. The elections are held using UDP, and then once the master-slave relationships have been established, the communications are all over secure TCP. Another point about network communication is we now support IPv6 for the management network. Okay, so let's talk about data store communication. So data stores are not used as a general communication mechanism. Rather, they're used to answer some specific questions that are needed in order to process a host failure. So let's go talk about that. So let's focus first on the master. So when a host becomes isolated, or rather when the master loses contact with a host over the management network, the master has to determine, is that host dead, isolated, or partitioned? So we use data stores to answer that question. In addition, when you have a partitioning or an isolation, it's possible that, or rather it's likely that the master is going to be responsible for some VMs running on those hosts. So the master needs to be able to monitor the health of those VMs, and it does through the data stores. The data stores we use for this purpose are called the heartbeat data stores. So this is a new concept that we're introducing in 5.0, and I'll go into that in a little bit more detail in a second. Now let's look at a slave. An isolated slave uses a data store to improve the isolation response. So when an isolated slave is deciding whether to power off a VM, it's going to check to see whether there's a master in the cluster that is taking responsibility for the VM. And it does that by looking at the data store that contains a configuration file for that VM. And we'll see how this comes into play when we talk about the isolation response. So heartbeat data stores. vCenter Server chooses by default 2 heartbeat data stores for every host in your cluster, and that information is pushed down to all the FDM agents. The algorithm gives preference to VMFS over NFS, and then for the set of data stores chosen for a single host, the algorithm tries to choose data stores backed by different storage arrays or different NFS servers. So therefore, we're trying to minimize your likelihood that you'll encounter both data stores going down. You can influence the decision vCenter Server is making, or you can constrain it by using the Edit Cluster Settings dialog in the UI. Of course, you can also do this through the API. Okay, so I've covered the two key concepts: FDM roles, responsibilities, and communication. Let's see how these come into play now. So the first we want to look at is a host that is declared dead by a master. So 2 criteria must be met in order for a master to declare a host dead. First, the host must not be in communication with the master over the management network. So what does that mean? It means the master cannot talk to the FDM on that host, and the master cannot ping that host. The second criteria is that that host is not issuing any heartbeats, data store heartbeats. In other words, the master cannot see that host through the data stores, the heartbeat data stores. So in this example here, we see host 4. Host 4 doesn't have management network connectivity to the master. It also is not heartbeating to the heartbeat data stores. So the master is going to declare this host as dead. When that happens, like in earlier releases, HA is going to restart the VMs that were last known to be running on that host. The master is going to place those VMs on either its own host or the host it's in network contact with. Okay, let's look at host partitioning now. There's 2 criteria, again, that must be met for a master to declare a host partition. First of all, the master is not in network contact with it. Again, that means it can't talk to the agent on that host, and it can't ping that host. The second criteria is that the master can see data store heartbeats from that host. So in this case, we have a cluster two partitions. We have host 1 and 3 in one partition and host 2 and 4 in the other partition. And so the master is going to declare host 1 and 3 as partitioned because it can see the data store heartbeats. Now, as I mentioned earlier, when you end up with a partition, you're going to get a master election. And so in this case, we see that the master was elected on host 3 as well. So one thing to note is that each master has its own perspective of the cluster. The master running on host 2 is going to believe hosts 1 and 3 are partitioned. It's going to report host 1 and 3 as partitioned. The master running on host 3 is going to report the opposite. When there is a partition, vCenter server is only going to be talking to one of the masters, and so it's only going to be reporting its perspective. The reason we architect it that way is we expect most times you end up with a partition that VC is only going to be able to talk to one master in any case, so there's no need to support it communicating with multiple masters. Now, as mentioned earlier, when you have a partition, it's very possible for a VM to be running on a host in another partition. Now, the architecture enforces that only one master is responsible for any given VM at a time. So that master may find that its VM is, as I said, running in the other partition. That's where the heartbeat data stores come in. By looking at the heartbeat data stores, the agent on the host write information in the heartbeat data stores, the masters consume that information, and on that basis it determines whether that VM is still healthy or not. If that VM should fail, the master will then restart it on its own host or the host it's network connected with. And of course, when a network partition resolves itself, all but one of the masters will abdicate. So let's look at the third failure. A host becomes isolated. The criteria for an isolated host is it does not observe any HA management network traffic, and it cannot ping its isolation addresses. That's the case for host 4 in the example here. This criteria is the same as in earlier releases. Now, there's an important point here. You may notice that I said for the failure case and the partition case that the master declares the host to be dead or partitioned. Only the host itself can determine whether it's isolated or not. As far as the master is concerned, an isolated host looks like a partitioned host. So we use the heartbeat data stores to have the isolated host tell the master that it is isolated rather than partitioned. So in earlier releases, when you had an isolation event, HA was reporting that host is dead. Because we can use the heartbeat data stores, now HA will report that host is isolated. Okay, when an isolation occurs, there's activity happening on the isolated host and on the master. So let's look at the isolated host first. As in early releases, when a host becomes isolated, it's going to inventory the VMs that are running on it. It's going to decide which ones need to be powered off or shut down. Now, for a given VM, before it issues a power off or shutdown, it's going to check to see whether there's a master out there that's taking responsibility for that VM. It does so, again, by checking the home data store for that VM. The outcome of this check, there's 3 outcomes for this check. It could find that there's no master responsible for this VM. It could find there is a master responsible, or it may not have access to that data store. Let's look at the first 2 first. So if there's no master responsible, the isolated host is going to wait for a master to become responsible. Only once there's a master responsible will that host shut down the VM. Now, in the third case, it has no access to the data store. And we have no way of checking to see whether there's a master responsible. And as a result, we're just going to apply the configuration that you've made, which is to shut down that VM. Now, we're doing this check to avoid the total cluster isolation scenario, because if you lose your networking, your entire cluster, all hosts in 5.0 are going to declare themselves isolated. No master is going to be taking responsibility. There'd be, first of all, no master, and so there'd be no one taking responsibility for the VMs. Therefore, as long as connectivity to the data stores is maintained by the isolated hosts, no VMs are going to be powered off. So this is the way that we're preventing a total cluster isolation event. If you have an environment where you're using NAS, then it seems more likely that you're going to end up with data store connectivity being lost at the same time an isolation occurs. There's really nothing we can do to prevent the VMs all from powering off. But to make you more aware that this is a possibility, we've changed the default isolation response to leave power on. So you have to make the explicit choice to change that and therefore go through the thinking process about whether you might end up with a total cluster isolation. Let's now look at the master. So there's 2 cases to consider on the master when there's a host is isolated. First, case is that both the master and the isolated host retained access to their heartbeat data, to the heartbeat data stores. I want to note that the master itself doesn't have to mount those data stores. The master can access them by proxying through any of the slaves connected to it or the management network. So if the master and the slave have access to data store connectivity, as the isolated host powers off VMs, the master is going to observe that and is going to restart those VMs. If, however, data store connectivity is not maintained, then we're just going to treat the host as dead, as we did in early releases, and just make an attempt to restart those VMs, and we'll attempt for 30 minutes. So as long as the isolated host powers off the VMs within 30 minutes, those VMs will get restarted. Okay, so you may notice when I was talking about the host failures, I was intentionally vague about which VMs are actually being restarted. So this is the topic of the third concept, HA protection and the failure response guarantees. So as you may remember from my first slide, HA protects against 5 types of failures, and these can be grouped into 2 categories. The first relate to what's happening in the guest. The guest OS could crash or hang, or application heartbeats can stop, as signaled by a third-party agent running inside the guest. In that case, HA will reset the VM. This reset VM action applies to those VMs that have VMware tools installed, are appropriately configured for the isolation response. Also, the VMs have to be running on a host where the FDM agent, or rather the FDM, has been properly initialized. Of course, like in earlier releases, if the VM tool's heartbeat stop, we are checking to see whether there's I/O activity, so we haven't changed that behavior. Now, if a host fails or a VM is powered off when it's isolated or a VM crashes, HA is going to restart that VM. Now, the master that recognizes that failure and responds to that failure is only going to restart the VMs that are HA protected. So HA protected is a new concept in 5.0. So to understand what HA protection is, let's look at the workflow that leads to VM becoming HA protected. So that workflow is diagrammed here with 7 steps. Time runs down the chart. So in the first step, we have a user issuing a power on for a VM. In the second step, we have that the host actually executes that power on. And in the third step, we have vCenter server learning about the power on. At that point, vCenter server will tell the master to protect the VM. That happens in step 4. In step 5, the first green blocks, the master is going to get that directive. Then it's going to go ahead and write a file on disk. It's writing a file for that VM. The file it's writing is the file that's stored on the home data store of that VM. Remember, the home data store is a data store that contains the config file for that VM. When that write is done, the VM now is HA protected. So now let's look at what the failure response guarantees are. Once the write has been done, HA guarantees that it will make an attempt to restart this VM. If the failure happens at that point in time or any point in time in the future, HA knows about this VM, so therefore it's going to restart it. If the failure happens anytime after VC learns about the power state change and anytime before the write is done, HA only guarantees that it may make an attempt. Whether it makes an attempt or not depends upon the nature of the failure. So as you'll notice from this workflow, this protection process is asynchronous with respect to the power on process. And because of that, we've introduced a per VM protection property. This property basically tells you whether or not a VM is protected. This is reported in the summary panel in the UI for the VM and also optionally in the VM list views for VMs. Now, this property can have 3 values. It can be not applicable, unprotected, and protected. So let's look again at that workflow and see how those values get mapped to the workflow. One thing I want to note is that I've added a step at the bottom. The HA protection property is reported by VC. It's VC's perspective on the protection. So the final step in the workflow here is the master telling VC that the write has been done. So the value of NA is used when the VM is running in a cluster that's not HA enabled. VM's running on a standalone host, or when the VM has just been powered on and VC doesn't know about it. As soon as VC learns that the power on has happened, and until VC learns that the write has happened by the master, the state is unprotected, telling you that if a failure happens, HA may or may not restart this VM. Once VC learns that the write has happened, we report protected. Okay, so in summary, I've talked about the 3 key concepts in the architecture and showed you how they apply in responding to host failures. Obviously, there's a lot more detail here. So after VMworld, you can download my slides. I've added quite a number of slide comments. There's also a large number of backup slides covering the UI changes, covering which files we're using for data store communication, where they're stored, what their sizes are. The backup slides also talk about how we've changed logging and how you can, the basic structure of the log file. So to summarize, HA allows you to run your business-critical applications with confidence. In 5.0, we've improved it in a number of different ways. We've simplified the management. We've made it easier to configure. We've given you greater flexibility in how to deploy HA. At the same time, we've made some of the existing failure responses more robust, and we've also added full support for partitions. Further, the architecture is much more scalable, so we think it's a good foundation for the cloud. Now, regarding how you can learn more about HA, well, of course, we're almost at the end of VMworld. This slide was meant for when I gave the presentation on Tuesday. But nonetheless, you can still go to the VMware booth and see a demonstration of HA. You can also go to the labs. Regarding documentation, so we've updated the availability guide. We've updated the best practices guide. A number of KB articles have been updated already. Of course, there's the release notes. A new document is called the troubleshooting guide. The troubleshooting guide covers some scenarios you may run into. For example, you may end up with a scenario where the VM remains unprotected for a period of time. So the troubleshooting guide explains why that might happen and sort of outlines the steps you can take to try to resolve that situation. And finally, I'm going to give you a little plug for Duncan Eppings and Frank Denneman's book. It gives a very good in-depth discussion of HA. It's presented in more of in a more sequential format, sort of explains the basic properties, etc. So thank you.
All right. Thank you, Keith. Thank you, Keith. My name is Jim Chow, and I'm an engineer working at VMware in the area of fault tolerance. And today I'd like to, well, it's my pleasure to talk to you about a little bit about fault tolerance. And I want to hit on two different things here. One is I want to describe to you briefly why you want to use fault tolerance, what makes it unique, special, interesting, so forth. And also, I want to demonstrate today a little something new that we've done in fault tolerance, something we've cooked up back in the labs in Palo Alto, and that's support for VMs with multiple processors, vCPUs. Okay. Oh, and before I begin, I should say, small disclaimer. There was a disclaimer at the beginning of this talk, and I just want to, again, sort of highlight that this is a technology preview, a technical preview. It's, it's a prototype back in the lab. We will neither confirm nor deny any of these features will ever be present in any product sold by VMware. So take that as a caveat. At the same time, though, we think it's pretty important and pretty cool, so we're going to show it to you today. Okay, so this is the portfolio of products that Keith was mentioning to you earlier in the talk, and fault tolerance plays a special important role in this portfolio, and the reason is because it's the only product that really gives you continuous availability. And what I mean by that are two specific things. One is zero downtime, second, zero data loss. And what that means is if you have a VM running on a host, a ESX host, and the host goes down, hardware failure, at the instant of the hardware failure, another VM that's essentially identical to the original VM it's instantly transitioned to that other host and picks up right where it left off. And no software inside the guest is ever aware of this transition at all. It can't observe any loss in the state of the VM at the time of the failover or notice any downtime. And so it's very much like vMotion in that sense, except a vMotion can take, potentially a minute for a large VM to happen. In this case, you yank the power cord on one machine, that VM is instantly transitioned to another machine instantaneously. There's no wait for a minute for the vMotion to happen. So it's very much the same guarantees that you get with a vMotion, in that there's no loss of TCP state, no loss of TCP connections, except that it happens instantaneously. Another sort of key point to this is that the fault tolerance is completely transparent to the guest software in vSphere. So that means that means two things. The first thing is that means no matter what kind of software you're running in the guest, it can be protected with fault tolerance. And so, you're running Windows, Linux, database software, Java software, legacy programs, they all work without any modifications. And the second thing this means is that there's also, unlike sort of clustering solutions, there's no software that you have to configure or manage inside the guest. So there's no maintenance or configuration that you have to do ongoing. With FT, all you do is you click a button, you turn FT on for that VM, and that delegates all the subsequent management directly to the virtual infrastructure. And so basically all the decision making as far as figuring out what other machine to pair up with your primary host to provide you with the redundancy, all that decision making is done by the virtual infrastructure, and when a failover happens, figuring out a new machine to regain protection and synchronize, that's all taken care of automatically. So there's really nothing for you to do once you turn it on. All right, so that's continuous availability. We're pretty excited about that. And so in 2009, vSphere 4.0, we had the first launch of the product, and subsequent releases, we added support for new hardware, et cetera, et cetera. Now, if you're interested in sort of seeing additional details about how the fault tolerance product works and sort of its requirements and so forth, you can go to the product page at VMware.com. Now, one issue with the existing fault tolerance product in vSphere is that it is only supporting uniprocessor VMs. Now, this is something most people may have noticed. And then they comment to us regularly, is this something that VMware is interested in doing, supporting multiple processors? I can tell you for sure that is something we're interested in doing. Unfortunately, we weren't convinced that a software solution was actually even possible for this problem. So it turns out sort of supporting fault tolerance for VMs in the same way that UPFT works is an impressively hard problem. And in the community of people that are interested in solving this in a software-only way, this is a famously hard problem. And what I mean by hard is it's not like, like writing your own operating system. You get enough people, resources, you throw it at the problem after a few years or whatever it takes, you're going to get an operating system out of it. This is sort of to the extent of, no matter how many resources you put at the problem, it's not clear there can be a good solution to this. So what we've done is we've had sort of some literally brilliant engineers working on this problem for a considerable amount of time, and we've had a number of breakthroughs over the the past so often. And back in Palo Alto, we've sort of reached what we think is a milestone in our own implementation. We're pretty happy about it. I should say, in all fairness, that there are hardware solutions to this problem that have, for various platforms and various software architectures over the years, been available for literally decades. But the story for software-only solutions is much less storied, I can tell you. But we think we can change that with the solution that we have today. So we have a concerted effort to try to solve this problem, and we reached something of a milestone. We would like to share it with you today. We think it's pretty special. So I want to just sort of give you an overview of kind of what it looks like. And to do that, I want to sort of contrast it what we've got with regular uniprocessor FT. So the picture is very much the same. You've got two hosts running on vSphere. You've got an FT logging NIC connecting them. They're running a protocol between them, which we call vLockstep, that synchronizes the two virtual machines and makes sure they have the exact same state. And we have shared storage between the two VMs. They actually share the same VMDKs. Okay, now we had to take a really clean slate approach when we were trying to tackle this problem. And we ran into a lot of difficulties when we try to look at the old approach and see how we can solve it for multiple processors. And so one of the things we noticed was that there's a lot more data that you need to deal with multiple processors than there are unit processors. A lot more data. And so one of the things we did was we sort of upped the requirement on our prototype. Our prototype uses a 10 gigabit Ethernet adapter for the FT logging NIC. And the second thing we did was we replaced the old protocol that was being used over the logging network. We replaced it with sort of a native multiprocessor supported protocol that sort of from the start it was built to handle a multiprocessor workload. And we don't have a fancy marketing name for it yet, so SMP protocol, that's what it is for now. And the last thing we did, very important, is we in the old realm we had shared storage. In this case, we don't want storage to be a bottleneck that we have to synchronize between the primary and secondary. So instead, we split the storage out, and what that does is give you one, that it relieves sort of a synchronization point, and the second thing it does is it gives you the potential for sudden redundancy. That's what the current prototype looks like. I'm going to spare you the details. I can say that this slide sort of massively understates the amount of work that goes into this protocol. That's where most of the work went into. But I can tell you that this architecture is continually evolving, so we're going to have to leave it for another VMworld, perhaps, before we go into a deep dive. Yeah, well, one thing, heard some boos on the cat calls, but one thing I think we would like to do is to see it in action. Hopefully it's still running. Okay. All right, so what we'd like to do is kind of give a little demo of what the system looks like. So we've got a VM, and it's protected with fault tolerance, and it's doing the SMP protocol. And we have a client out there. It's not protected. It's just a regular Windows client. It's going to connect to the VM. It's going to issue a bunch of queries to what we have protected is a database server running Oracle. And it's going to do a bunch of queries. We're going to fail over. We're going to cause one of the hosts to come down, and it will instantly transition to the other virtual machine. Now, I should say this is a sort of experimental setup. There's some caveats. It's a prototype, so we'll see what happens. So I need to switch over to here, and we'll see what happens. Okay, that's mostly what it's supposed to look like. Okay. First things first. So this is the client machine, so Windows. I've already protected the Oracle VM. So I'm going to log into it. It's this guy. So I'm SSH'd into the VM. I'm going to do this. It's running RHEL 4. Okay. So we see that there. And it's like a 32-bit VM. It's got about 4 gigs of memory, something like that. Let's see what's running. Pretty much nothing's running here. Let's take a look at the CPU count. We've got about 4 virtual CPUs. Not much going on here, so I'm just going to put that window to the side. And then I'm going to start up another session. Now, this is the primary here. It's supposed to be color-coded. Unfortunately, I'm not sure how well that comes out. It's supposed to be red background, red for the primary. I'm going to run ESX top. We can see that the VM is indeed running here. I'm going to take a look at the networking. So here, VMNIC 4 is the 10 gig NIC that's running, that is doing the FT protocol. You can see consuming about 60 megabits. Okay. So not a ton, but not nothing. So I'm going to put that off to the side for now as well. Do that. And then I'm going to log into the backup. So this is the secondary acting. Secondary, I'm going to take a look at ESX top. We're going to look at the VM. We see it's running, not doing a whole lot. So we have 2 different hosts there, primary and secondary, being synchronized. Okay, now I also have a workload generator here. This is a Java program. It's going to generate queries to the Oracle database. Now, this is all happening on a client machine, Windows machine, completely separate machine, not FT protected. All this is going over the network. So start that up. And these graphs, these charts, are basically showing the queries being executed against the database. That's starting to ramp up. Now we take a look at what's going on in our SSH session. We can see, yes, it's starting to ramp up. Oracle spawned a terrifying number of processes, and this is CPU is going on. Okay, so that's basically what we'd expect. Now let's go over to the primary here. This guy, we see 600 megabits. That's starting to ramp up, and we'll see, there it goes at about 2.4 gigabits. So the workload's starting to execute. Things are happening. I'm going to put that to the side. Go over to here, back up, stuff's happening. Okay, now, what I'd like to do at this point is do something most system administrators probably wouldn't want to do, and that's I'm going to bring down the host that's running the primary workload. Normally, that would be a catastrophic event for the workload, and somebody using it, running this query generator, will notice and probably file a ticket or call you or something like that. The magic of FT, that hopefully won't happen. Now, before I press enter here, I just want to say one thing, which is this is a developer prototype. I compiled it last week, literally compiled it last week, and I can say that I've seen it fail. It does fail. It does fail. It can fail. I've seen it fail, and when it fails in strange and shocking ways, and when in ways that potentially make you ashamed to put your name, associate yourself with it. But I can tell you, we did the session on Tuesday, and it worked flawlessly. So if things go horribly, horribly south, you can find yourself someone who went to the Tuesday session, and they can speak in hushed, with wonder and amazement at how well the thing worked. But whatever doesn't kill you makes you stronger. So let's go ahead with this and press enter here. Now the putty session for the primary has gone down. Now we would expect that to happen because the machine has gone away. Let's take a look at what happens here on the secondary. All right, the VM still there, running. I'm going to take a look at this SSH connection. You can see we can continue typing here. The top is still going on. You can do here. SSH session still going, strong. And take a look, and this workload hasn't missed a beat. Keeps going. So that, yeah. I wasn't sure that was going to happen either. So, all right, I think it's time to quit while we're ahead. All right. So we've what did we just see there? We saw SMP FT in action. We think we have a pretty good solution there, as we just saw. And there's one thing I want to point out, that the clients to the VM were completely oblivious to the fact that we rebooted the host that the VM was running on. And there were two clients in that demo. The Swing Bench client, the Java thing working, the graphs and everything. And then the second one was the SSH client, that, you're typing stuff. That client, you could continue to type, no problems, keep going. No one was the wiser. So transparent failure, we saw the zero downtime and stuff like that. And we got a taste for sort of the performance characteristics. I mean, you could see, you didn't really notice a big difference when you were typing at the console, and you could see the bandwidth that was being used on the 10 gig NIC. For that workload, it was like 2 to 3 gigabits or so when it was ramping up. So that's basically what we did. But of course, we've seen the demo here. I wanted to give you a taste for what it looks like, but I also want to try to make it a little bit more concrete. We've actually run this system on other workloads. So I want to give you a summary of some of the stuff that we've tried so far. In vSphere 4, we published a white paper that showed a bunch of workloads where we ran FT, and we had a bunch of numbers, graphs, and so forth. So we took a few of those workloads in a similar configuration. These are ones that are supposed to model real-world workloads. So they're like these macro benchmarks. We configured them for 60% CPU utilization, and there's the same configuration that they had in the fault tolerance, the original vSphere 4 white paper. So we want to see how this would look like in this system, except we add vCPUs. Okay, so on the left here, we've got SQL Server 2 and 4 vCPUs. We've got Oracle Swing Bench, the demos we just saw, and 2 and 4 vCPU configurations. The bars represent the sort of the end score that you get when you run the benchmark, and it's a percent, the FT score versus the non-FT score. And we see that there's some overhead, right? You don't get the FT for free. When you turn on FT, this protocol that's synchronizing the two VMs that consumes some CPU time. So it's taking up a bit of your performance. So we're at right around around above 70% for a lot of these benchmarks. For the 4 vCPU Oracle one, we're sort of under 60. So we got a bit of work to do, but that's sort of give you a flavor of what we're looking at. Okay, so I just want to sort of summarize the FT portion of this, so I sort of described why you'd want to use fault tolerance, what makes it interesting. It gives you continuous availability, and it's a very strong property because no one is the wiser when a failure happens. And I also showed you fault tolerance for multiprocessor VMs. And there's an impressively hard problem. We think we have a very good solution here, and it required a new design, which is sort of outlined, and sort of demonstrated a little demo. You can see it in action for yourself. A very similar experience to the uniprocessor FT. Just click a button, turn on FT, and things are working, except more vCPUs, which is a good thing. Okay, so. That sort of is the HA and FT portions of it. I just want to talk briefly about sort of some future things in the HA-FT space that we're looking at. One of the things is there's sort of two broad directions that we're looking at for in the future. One is sort of to cover more kinds of failures. Now, in the FT case, what we just saw was a hardware failure. You bring down the host, and you can transition to a working host. That's one type of failure, but you can imagine there are other kinds of failures you might want to handle too. So, for example, if one of the hosts doesn't have connectivity to an important resource, like storage or something like that, you can imagine that would be a reason to fail over to another host, et cetera, et cetera. So, there's connectivity to important resources. That could be a reason. So host component failure is what that says over there, and similarly for HA. And the other thing we want to do is sort of expand up the stack the kinds of failures you can support. So we support hardware failures, that was sort of just demonstrated, but we want to sort of create new APIs to handle failures like application-level failures, et cetera. In vSphere 5, for example, HA has a new SDK that lets you handle application-level failures, to define those at application level. And we want to expand that. For example, for multi-tier applications, you can imagine specifying even beyond a single VM that there are like multiple VMs that you care about, and that if any one of them goes down, then that could be a reason to fail over. So we're looking at expanding that, trying to handle more cases, and the upshot of that, and then those APIs, et cetera, are going to enable different people to extend our solution. The upshot of that is that we can handle a lot more failures and sort of be a complete availability solution. Okay, so that concludes the talk part of the talk. So we're going to do some Q&A. If you do have a question, it'd be good to come up to the mics. And thank you. What's that? Yeah. Why don't you go ahead?
Two questions.
Yeah.
First off, the current restriction in VMware FT having to do with second generation hardware assist MMU. Any hope to see that resolved?
For the existing FT, you're saying?
I'm curious about the future.
Yeah, okay. So, yes,
with respect to the SMP FT is really what my interest is.
Yeah, in the future, we plan on taking advantage of all the hardware assists that are available to us and that give the best performance for the VM. That's completely the case. And with the current solution, there are some limitations, I understand, but the future one, well, yeah, that's...
All right. The second question is, ostensibly the concepts that you laid out here, it would look like that this is not restricted to 2 vCPUs.
That's correct. And the demo was 4, yeah. But, yeah, there's actually no limit to the number of vCPUs, but as you can imagine, the amount of bandwidth that's required on the link scales sort of linearly with the number of vCPUs. So,
thank you.
Uh-huh.
Are there going to be changes for the backup API for the FT so that products like Veeam can back up an FT?
I don't know. Yeah, sorry about that. Yeah, I can't comment on that, unfortunately.
Real quick question. Just like vMotion, you can do multiple NICs now for vMotion. Is there any way or any thought of letting that go for fault tolerance so you don't have to have a 10 gig connection?
It's something we're thinking about. Obviously, it's just bandwidth that we're concerned about, getting enough bandwidth. And as you saw with that demo, we got around 2 to 3, under 4. So you can imagine teaming like 4 gigabit NICs perhaps. We haven't played around with that too much. We've mostly stuck with the 10 gig, but that's, it's possible.
It's a concept that's been thought about.
Yeah, I mean, we've definitely tried it. It's not something we've, done a lot with. Thank you.
The new SMP architecture that you described included a shift away from shared disk to unique disk for each VM. Will that change also be happening for the existing FT implementation?
This was specific to this prototype. I would say that's not in the works for uniprocessor FT for right now.
Okay.
Yeah.
Hi, thanks. First of all, it's a great product, seriously. So in the old days, still now, there is a recommendation to put up until 6 VM per host when you're using fault tolerance.
Okay.
So is that going to change? And the second question is, what was the latency or the performance overhead that you observed on the guest itself? Because you could imagine people who will want to use it for mission-critical application where every bit of the CPU performance is extremely important.
Yeah. Is it 6?
It's 4, actually.
Yeah, it's 4. The current limit is 4 FTVMs on a host. It's a prototype, so it's not a product. It's hard to comment on, specific limits. In this demo, we saw that we were consuming, a considerable amount of the 10 gig NIC. So the thinking is maybe, you wouldn't have many SMP FTVMs per host, like maybe 1, for example. But that's, again, it's a prototype that has yet to be fleshed out.
I'm sorry, I interrupted you.
Yeah.
I was just saying, is your question specifically about SMP, or is it also about UPFT?
FT and SMP,
yeah. So, and then your other question, what was the other question? Is about, latency. Yes, there is latency, a measurable latency on the workload. And for a highly latency sensitive workload, that it would be a concern. It's hard to broadly characterize it, so you'd have to run your workload and see if it works. But latency is definitely a big issue. I mean, this is something such a big thing that we'd publish a bunch of numbers to show what the latency effects are. We've mostly been concerned about bandwidth for the most part, but latency is definitely an important thing.
Thank you.
Yeah.
Hi, question about FT. I saw you log into the primary and the secondary.
Yeah.
Was that so the secondary was on the same ESX host?
The secondary was on a different ESX host.
Right. So
yes.
So you just logged into the ESX host and you saw that the VM was running, right?
Yes.
So we can't log into to both the primary and secondary at the same time, right? We can't access both the machines.
I did do that.
Okay. So that means that both the VMs are online. They have different IPs?
No. It's like vMotion, right? When you vMotion a machine from one host to another, it doesn't change IPs. It has the same IP. So in this case, when you have 2 VMs that are being FT protected, they have the same IP. Just one isn't alive. One is alive. And then when you kill it, the other one becomes alive.
Yeah, and all the security and OS patches go down to both the VMs because the same VMDK, right?
Yes, exactly.
Okay.
Well, in the SMP cases, it's separate VMDKs, but it is true that they're perfectly synchronized so that any change you make to the first VM is automatically, going to be present, on the second VM. So, if you reinstall the guest, you were running Windows, you install Linux. When it fails over, you're going to be running Linux on the other side.
That's right.
Yeah.
So, what about another question? What about multiple VMDKs?
Multiple VMDKs.
Multiple VMDKs?
Yes, it supports essentially any number of VMDKs.
All right, thanks. That's it.
You're welcome. Question on the left here, or you're right?
Okay. VMware HA kicks in only when there is a host failure, right? If the host is still live and if VM hangs, in that case, VMware HA will restart the VM on the other host?
If the VM hangs in the sense that, for example, the data store goes out from underneath it, is that the scenario you're talking about?
Sorry?
When you said the VM hangs, I'm just trying to get clarity as to what kind of hang you're talking about. Like, the data store goes away for that VM on that host?
No data storage, just VM on the network layer hangs.
So you mean that? Are you saying that the guest OS?
Yeah, guest OS hangs.
Right.
Yeah.
So if you've enabled VM application monitoring, then that should trigger a reset of the VM, cause the OS to boot again.
Oh, okay. So we need to turn on the VM monitoring.
Application monitoring, that's right.
Okay.
Yeah.
Thank you.
HA, what is the Heartbeat data store looking at, or HA looking at, to verify that VM is still running? Is it one of the files of the VM, the VMX file? Or?
No. So there's a couple of responses to your question. So first, let's talk about how the master knows the host is alive or not. So we're viewing heartbeating through the data stores. If we're using a VMFS data store, VMFS does heartbeating naturally. So basically, the agent is opening the heartbeat region, accessing the heartbeat data on the master's host, is opening the heartbeat data on that data store, finding out whether the host is still alive. So that tells the master that whether the host dies or not. If we're using NFS data stores, the FDMs do implement heartbeat themselves. We open a file and we touch it periodically. So that says whether the host dies. Now, what if the host is still running? Each FDM writes to a file in the heartbeat data store that lists the VMs that are actually running on that host. And actually, that file also has a bit in it that says whether the host is isolated or not. So as VMs power on or power off, that file gets updated. So the master is reading that file and comparing the versions, the previous version to the current version, and seeing whether VMs are disappearing from the host. And if so, it knows that a power event has happened. It doesn't know whether the VM failed or not. So it's going to, as part of the restart process, it's going to discover whether that was a user power off or it was actually a power off because of a failure. And these files are stored in a root directory on the data store. You'll see a .vSphere-HA directory. Inside that directory, you'll see a directory per cluster. And then that directory contains these files.
Thank you.
What kinds of application monitoring do you support and provide?
Today, so what we support today is we have this API in the guest that you can have a third-party agent or an agent you write yourself that basically issues heartbeats. And you configure HA that when those heartbeats stop, the HA will reboot the OS. So this is what we support today is basically that API, and then Semitech has developed their application HA solution that uses that API. And in 5.0, we've made the SDK available so you can write your own solutions or use a third-party solution.
Sorry, did you say the API will be available in 5.0? Or?
It is available. It's there's an SDK. If you send me a message, I'll send you a pointer to it.
Thank you.
Earlier, you were talking about how the two VMs in the fault-tolerant solution have to be pretty much identical, the same IP address and all that kind of stuff. To what degree do they need to be identical? I mean, do they have to have same number of virtual CPUs, everything? And then more specifically, in the context of creating those, do you clone them, or how do you ensure that they are identical? Can you speak to that?
We could take it. Okay, I'll answer this question, then we'll take all the other questions offline. Yeah, it is actually not your responsibility. When you turn on FT, the system will make a clone of the VM, make sure it's completely identical. There's no work to be done on the user's part. Okay, we're going to take the other questions offline. Thanks.